Okay, so here we go, number 2. Here's y equals e to the x, here's y equals 5. And the y-axis, so we're talking about this right here. That's the region that's bounded by those three things, e to the x, y equals 5. And we're going to rotate that about the x-axis. So the reflection would be down here like this. And we're going to get something like this. Or this is straight here. This is straight. Okay, just good so far? Make sense? Okay, so we need a typical, we're going to do a vertical slice, and that's going to make a washer, right? And so what will that washer look like? It'll look like this. Something like that. And so that's what we want the volume of a typical washer. So that kind of came out backwards. Let's see. What do I want? This. There we go. Okay, so it's supposed to be round, okay? But that's the general idea. So we need the volume of that thing, which is going to be pi r outer squared delta, or h, minus pi r inner squared h. And what is h? Delta x. So we need the outer radius and the inner radius. So the outer radius will just be from our axis of rotation up to here, which is always 5. That's our outer radius. Our inner radius will always be from there to there, which is our y value of this curve right here, which is e to the x. And we're going to add all those up from 0 to what? So we need the x value that gives a y value of 5. That's natural log of 5. So we're going to go from 0 to natural log of 5. And we're going to add all these up. So it'll be pi times 25 minus pi times e to the 2x dx. Okay, and I just said set up integrals. I saw lots of you solved them. I guess it's okay, but that's not worth any points. I just want to see the right integral. Okay, questions on that? Success? Some people get it? I see some nods. Okay, good.
It's supposed to be plus 1, right?
What's that?
Is it supposed to be 5 plus 1?
No, because we're rotating around the x-axis, and the distance from the x-axis up to 5 is just 5. If we're rotating around -1, then it'd be 5 plus 1. If we're rotating about y equals -1, and that would be e to the x plus 1. But if we're rotating around the x-axis, we just want the y coordinates of the points on these graphs, which are just 5 and e to the x. Does that make sense? Other questions? Yeah?
How did you get ln?
So that's just solving this for x. So it's the exponent of e that will give 5. That's a log, right? That's the log base e of 5. Or the exponent of e that would give you 5. The exponent of e that would give you 5. And that's natural log. So that's... But that's only a fraction of the... This is the most important thing, and then that would be secondary. Important, but not as important. Okay, other questions?
That's pi times 25, right?
Yeah. Okay, so we're going to move on to, so we're going to keep doing more solids. This is still some stuff from 7.2. You can take, so instead of doing solids by revolution, there's another way to form solids, and so let's see an example of that. So find, let's say, find the volume formed by square slices can never remember how to spell perpendicular. Perpendicular to okay, so this is not a volume of revolution, but it's a volume that we're going to form with square slices, squares, okay? So first we're going to need the region. Just like before, we find the region first and then the volume from that region, okay? So y equals sine x from 0 to pi, hopefully should be familiar. That's this. Okay, and then let's see. So to the x-axis and the region. Okay, so there's two ways to form. So here's our region. There's two ways to form square slices. So we could do like horizontal square slices, or we could do vertical. So now I'm saying perpendicular to the x-axis. Perpendicular to the x-axis. So that would be vertical, right? So what we're going to do is we're going to take a typical rectangle like this. Do red. And then instead of rotating this region, we're going to form a square that has that as its side length. So a square slice. So imagine this coming out at the board at you. So let's do this, right? This is standing off the top of the paper like this. So now this would go away. We can do it. So that's coming off, it's perpendicular to the region. And it's the shape of a square. So I'll draw it again in a second, but it's like if you imagine that region flat on the table, and then you have all these squares standing up on that region. The square side length is determined by whatever the y value of sine x is at that x coordinate. So these squares are going to start small at 0. Then the maximum size square is going to be here, and then they're going to get small again. So let me see. I'll draw it and see if you can see how I do here. So now I'm going to draw it like this. So now it's flat on the table, right? So So let's do the square right in the middle. The biggest square would be right in the middle there at pi over 2. And then you'd have, as you move this way, those squares would get smaller according to the y value of sine x until you had like 0. So it's all going to come to a point right here. Little teeny squares here getting bigger and bigger. And then, again, getting smaller and smaller to a point right there. So in the front, you're going to have a reproduction of sine standing up because you'll have all those side lengths that are the same as y equals sine x. So in the front, you're just going to have y equals sine x like this. Okay, and then from here, it's going to wrap around to that back corner like that, and then it's going to come back that. And so I'll draw another square in here. So there, for instance, there would be a square like this. It's supposed to be a square. And there'd be all squares, right? Starting from here, little teeny squares getting bigger and bigger and bigger and bigger until you get the biggest square at pi over 2, and then getting smaller and smaller and smaller again. So can you imagine that volume that you would get for that, kind of? So now we want to set up an integral to get the volume of the solid. So how are we going to do that? Just like we've done all these other problems. What are we going to do first? Volume of a typical, what is this? Butter pad. I just made that up right now. So it's volume of it's a square tile. So we'll call volume of the tile. Typical tile is going to be, so what's the volume of that thing? Side length squared times height. What's the height? Height is going to be delta x. So we're going to have side length squared delta x is the volume of one of those tiles. Because it's a square by a little thickness, right? So what is the length of our side length? What is our side length determined by? Yeah, it's going to be that dimension right there, which is y, which is sine of x. So we're going to have sine x squared delta x. So that's the volume of a typical tile, and we're going to have all the tiles from what to what? Yeah, the first tile will be here at 0, and then we'll have all the tiles, the square tiles, stacked vertically, starting at 0 all the way to pi. And the volume of each tile is sine x squared dx. Okay? How do you integrate sine squared x? Everyone should know. 1 minus cosine squared, right? No, 1 minus cosine squared just puts you in the same boat that you're in, right? It's half angle formula. 1/2, 1 minus cosine 2x. Okay, and then we can get that's the volume of that solid, right? Adding up all the volumes of the square tiles that change size as you go from 0 to pi, according to sine x. Okay? Questions on that? Yes, please.
How did you get the volume?
The volume of the tile? Yeah, so it's a rectangular solid. So it's like length times width times height. It's just like a box. because they're square tiles now instead of discs, instead of pancakes. So it's just the volume of a box is length times width times height. But they're squares, so those are the same. So it's basically that. Did that answer it? Other questions? Okay, so we can use this technique then to derive formulas for geometric shapes. So we can use this technique to derive the volume of a sphere. So let's do that. So here's how we're going to do that. So we could do this by rotation. Okay, so let's set it up. So if we want a sphere of radius r, okay, so let's set up. So what we're going to do? We're going to start with a circle of radius r. Or let's just go with a semicircle. Okay? So we'll go with a semicircle of radius r. So this is r0, 0r, and negative r0. So how could we use the technique from before, the technique of rotation, to get the volume of the sphere? What would we do? What region would we revolve around what?
That region around the x-axis.
You must revolve the region I'm showing you around the x-axis. So this whole thing. So that you do the top half of a circle and the x-axis, and then revolve that around the x-axis, and that'll give us a sphere. Totally valid. But we want to practice this other thing. Let's see. Shoot. Oh, yes, it does. Yes, that's right. So instead, what I want to do is, instead of doing revolution, I want to take semicircular disks and stack them perpendicular to this region. Okay, so I'm going to take a slice like this. And I want to imagine, instead of doing a square, so imagine a square not a square sticking up, but now a semicircle sticking up. And I'm going to do all those semicircles starting from here up to there, and that will give us half of a sphere. Do you see that? Yeah. Yeah. Thanks. Okay, so let me try to draw that. So like looking at that flat. So that's this thing flat on the table. And so my typical deal here is I'm going to take that thing and I'm going to do a semicircular disc.
Wouldn't that only give us a quarter of a sphere?
Maybe. That was, yeah. Let's see. Yes, that would be a quarter, right? So that's going to give us a quarter of the sphere. So here is where we're going to have the biggest one, right? So I'm going to have the largest one here. And then they're going to get small. Those half discs are going to get smaller and smaller until we come to this point at the top of the circle where you have it'll be like 0. So that'll give us a quarter of the sphere. Really make this disappear like that. And then this like this. So do you see if we stack those vertically, starting with the biggest one going back, we're going to get a quarter sphere there. So rotation would work around the x-axis, but we want to practice this other technique. So we're going to take a typical one of these right here, and we need to find the volume of it. So what's the volume of, this is a typical semicircular disc. How am I going to get the volume of that thing? What's the volume of that semicircular disk? So it's right. It's going to be half the area of a circle, and then times this thickness here, right? It's going to be 1/2 area of a circle, which is pi r squared times thickness. And this thickness is going to be delta x or delta y? I'm going to do delta y, right? So now I need the radius of this semicircular disk, which is going to be what, from here to here, which is x coordinate or y coordinate? X coordinate. So I need that x coordinate in terms of y. How am I going to get that? Well, I need the relation, I need the equation of this right here. What is the equation of this curve right here? Yeah, it's the circle centered at 0 with radius r, which is x squared plus y squared equals r squared. And so I need what x equals. What does x equal? X equals square root of r squared minus y squared. I didn't do this before class today, so I'm crossing my fingers that it's a doable integral for us, okay? I'm pretty sure it is. Okay, so that's x, and that's our radius, right? That's not this r. That's changing radius of our disks, right? This is a fixed number. This little r here. So maybe I should have. This is not the same r here. So let's use capital R. Capital R means the changing radius of our disk, of our typical disk, as we move up here from 0 to r. And we said that that's the x-coordinate, so that's this thing right here. And we just found that that was the square root of r squared minus y squared. Are we good? So we're going to add all those up, starting with the biggest one here at what, y equals 0, and then they're going to get smaller and smaller until we come to a point here at the top of the semicircle. So we're going to add those up from what to what?
0 to r.
0 to r. Little r, right? And then this is nice. The square root squared is just that thing. So I think we're okay. We can do it. Easy integral, right? And we're expecting the value of this to be what? 1/4 of the volume of a sphere, right? This is cool. So here we go. Let's see if it works. So we have 1/2 r squared with respect to y. What is that? 1/2 r squared y, right? R is just a constant, okay? Minus y cubed over 3. And we're going to go from 0 to r. I'm feeling very hopeful here. And this is a case where 0 is going to make that stuff 0, so all we got to do is plug in r, right? So 1/2 r squared times r minus r cubed over 3. Still doing good? So we've got 3/6 r cubed minus 2/6 r cubed. Did you buy that? Am we good?
I thought the R's were both different.
What's that? So this whole thing right here was our capital R. It's in terms of little r. Yeah? Yeah.
I think the 1 cubed over 3 was supposed
How come? Oh, did I forget the 1/2? I forgot to distribute the 1/2.
So when the pi?
So is this 6?
6.
Thank you. And so this is 6. Is there another mistake?
Yeah,
That's
pi.
fine. Pi will be outside of the even the
Good thing you guys are here.
you can do one. Yeah. Pi outside.
Is this okay?
Mhm.
All right. So
Can I just take the left and the pi outside?
yeah, let's start over. This part. Too many mistakes and changes. Okay. But I'm feeling very confident here. Yes, I like that idea. Let's take the 1/2 pi out, all out. 1/2 pi times r squared y minus y cubed over 3 from 0 to r. Okay, stop. Let's do each step, make sure everyone agrees. We good? Is that right? So 1/2 pi times, is that r cubed? Minus r cubed over 3, and then it's going to be minus 0 plus 0. Still doing good? So is this 2/3 r cubed? Is that right? 1/2 pi times, that's much easier. Which is 1/3 pi r cubed. Did we get it? We got it. Because what's the volume of a sphere? 4/3. Volume of a sphere is 4/3 pi r cubed. And we got 1/4 of it. That's what we were expecting. 1/4 of the volume of a sphere. So times 4.
When's the times 4?
What's that?
The times 4?
Just because this isn't the volume of a sphere, it's the volume of a quarter sphere. We found the volume of a fourth of a sphere, right?
Mm-hmm.
So I'm just showing that if you took our answer times 4, you get the volume of a sphere, which is the formula we already knew. So this is the value of our integral, which we knew was a quarter of a sphere. Okay, so you can derive a lot of the common geometric formula, volume formulas, using these techniques by slicing it up, doing the integral of a typical slice across the volume, and then it gives you, if you do it right, you can derive these formulas. Any questions on that? And this is an important technique. We're going to get to applications, and so some physics applications, and this kind of thinking is really important. Questions before we go on? Yeah.
With the r squared to the r squared y right there, how did you get to that? Because I thought when you took the integral, it would be 1/3 r cubed.
No, because it's r is a constant.
Oh, okay.
And you're integrating with respect to y.
Okay.
Yeah. So it's just like a number like 4, right? Or 6. And then it's going to be 6y. Other questions? Yeah?
I didn't understand how you moved from the first figure to the second figure.
So we're going to start with this down here, right here, is what I drew up here. So I just took this semicircle disk and laid it flat. And then in order to get, one way to get, in this case a quarter sphere, would to be do semicircular disks that are perpendicular to that. So they're sticking out of the board. So you've got half disks sticking out of the board. So you got a really teeny small ones here getting larger and larger, like that. And so now, I'm taking this whole thing and I'm laying it flat and showing you those disks sticking off the region that would be coming off this way. Is it better?
Yeah.
And so then we took a typical volume of a typical disk, which was 1/2 pi r squared, times the thickness of it, delta y, which is right here. And then we got that, and we added them all up from 0, so the largest one here at 0, all the way to r, where it like kind of disintegrates into nothing. Other questions? Okay. So let's go on to the next section. So what were some, do you guys have your notes from yesterday? What were some examples we did yesterday? Let's take a look. That was the very first example we did yesterday.
Oh, that was
homework.
This one.
Okay. Hershey's Kiss. And that was y equals x squared and x equals 2 about the x-axis. Okay, and what was our integral that we got for that?
0 to 2 pi.
Well, let's just do it. Let's just do it again real quick. All right, so we're going to do y equals x squared, x equals 2. We're going to do the x-axis, so that's going to look like this. And we did pancakes that's stacking this way, right? So volume of a typical disk was what? Pi r squared h, which was pi, just the y coordinate, delta x, and the y coordinate was? This should be really easy now, after all your practice. So the volume of the pancake was pi x squared squared delta x, and we're going to add all those up from 0 to 2. Okay, so if we actually evaluate this now, it'd be pi x to the 5th over 5 from 0 to 2, or 32 fifths pi. Did I make a mistake, or do you agree with that? Feel okay? All right, so that volume of that Hershey's Kiss was 32 pi over 5. So now we're going to do this a different way. Let's try, can we do this using, is it possible to do this using horizontal slices? Same problem. The question is, when you take a horizontal slice here and rotate it about the x-axis, what do you get? Do you get a washer or a disc? Okay, so you imagine this thing being rotated around the x-axis. So when it gets tiered down, and it'll be like this, and we're rotating this around like this. So do you see that this is like a different kind of thing than we had before? So it's totally hollow in the middle, right? It's totally hollow. If you imagine that little rectangle rotating around the x-axis, you get like a sleeve, right? A thin sleeve, and they call this a cylindrical shell. So the first shell here at 0 is going to be really tall and have a really hole, like a straw. This first one's going to be like a straw. And then the last one's going to be really short and have a really big hole, right? You see that? This last one here, when we get to up to the top here, it'll be a real short, squatty shell with a real, it's like a ring, right? Like a big ring. Whereas the very first one will feel like a long, like a straw, like a real long, narrow with a small hole in the middle. And then all the ones in between, okay? So we should be able to, if we can get the volume of a typical shell, add all them up from 0 to what? To 2?
Yes, correct.
Well, let's just do let's get our volume first, and then we'll worry about that. Okay. So the volume of a typical shell. How are we going to get the volume of that thing? No, it's a little different than the washer. So
Like cylinder?
it's a cylinder, but it's a hollow. It's totally hollow. It's like a sleeve, right? It's like a sleeve. So here's what we're going to do. We're going to cut this thing. Cut it right there. And then I'm going to unwrap it. And what shape will I get when I cut that thing and unwrap it? It'll be a rectangular solid, right? It'll be like this. Okay? And what will the dimensions of this thing be? So you imagine I just cut that thing and I just unrolled it and flattened it on the screen. So what is this dimension right here? What will that dimension be right there? So that'll be from here to here. Okay? So 2 minus x squared. It's a change in x, right? It's a change in x from here to here, which would be 2 minus x squared. Okay? What will be this dimension here? So now remember, I've cut it and I've unrolled it. It's going to be the circumference of this circle, 2 pi r. And what is r? What is r? R is the distance from here to here. That's y, right? R is y. So 2 pi r, which is y. And then what is the thickness of this thing? So we started with this right here. The thickness is delta y, right? We started with a horizontal slice. So we need to get everything in terms of what? X or y? Y. Okay, so we're good here. 2 pi y. Our radius is y, so we need this. 2 minus x squared. What does x squared equal? We're on this curve. What does x squared equal? No, that's just y. X squared is y. You see? Just 2 minus y. Wait a second. No, this is not x squared. This is 2 minus x. So all of you are saying this is not 2 minus x squared. Okay, it's final x 2 minus initial x. I knew something was wrong there. So this is not 2 minus x squared. It's 2 minus x because it's just the x value at this point on the curve. So sorry about that. Does that make sense? That distance is 2 minus x, not 2 minus x squared. X squared is a y coordinate. So we want the final x minus initial x to get that length of that thing right there. So then you're right. So it's equals 2 minus x equals 2 minus that squared y. So the volume of the cylindrical shell then is base times length times height. Okay, which is just going to be, the volume of the shell is going to be 2 pi y times 2 minus radical y delta y. Okay, I'll stop right there. So this is the crucial. That's the hardest part right there. So did I lose you? Any questions before we go on? Okay? So we're going to add all those up from what to what. So we're doing y now, right? So we're going to add all those shells up, starting with a straw, right? All the way to the real low flat ring. All those in between, from 0 to this y value right here, which is where x equals 2.
16.
Nope,
Was it 2?
nope. Where x, the y value where x equals 2. 4. Right? It's on y equals x squared at x equals 2. So y is 4. So I'm going to, yeah. So I'm going to distribute and do the antiderivative in the same step. So I think this is going to be, let's take the 2 pi out just completely. So this is going to be y squared. And this is going to be what? Y to the 3/2. So minus 2/5. Y to the 5/2. It's going to be the antiderivative. And we're going to go from 0 to 4. Check my math, right? Y to the 1 plus y to the 1/2 is 3/2 raised power of 1, 5/2, 2/5. I think that's right. Okay, so we're going to have 2 pi times 16 minus square root of 4 is 232 64/5. And this is 80/5 minus 64 is 16/5. So 2 pi times 16/5. 32 pi over 5. Which is the same exact, same solid, same volume, right? Just different way of doing it. Don't worry, so you can do this later, okay? So if you're not seeing these last steps, do later, okay? The setup, this is what we're going to focus on. You can take some time to get this yourself, okay? But the setup, from doing the typical slice and the setup of the integral, that's what we should be talking about. Questions? I lose you. So in this problem, if you didn't specify, this is much easier, obviously. But there's going to be problems where shells are going to be a lot more convenient and easy. Okay? So you wouldn't choose to do it this way for this one, but we got to learn it. So it's a good example to show that you get the same volume, regardless of which way you do it. Questions? Anybody? Okay. So let's do another one here. So let's do y equals e to the negative x. The x-axis. X equals 2 and x equals 5. Rotated about the y-axis. So first see if you can sketch that solid. Can you sketch that solid? First of all. Okay, so your region is like this. How about using discs or washers for this? How about using discs or washers for this? You do a washer. Now, what about using washers for this? What happens? You see? Do you see that this would be the inner radius, but what about the outer radius of our washer? What's that?
Both constants.
No. It changes, right? Look up here. For your washers up here, inner radius would be 2, outer radius would be the curve. But when you get down here, inner radius is 2, outer radius is 5. So you have to split it up. You're going to do washers here. It's actually 2 different solids because the outer radius on the top of the solid is defined by this curve, and then toward the bottom of the solid is defined by that vertical line. So here's an example where it's to your advantage to use shells. Shells, you just do it one time, right? So your shells are going to be, is it going to be delta x or delta y? Delta x, okay. So we're going to start with a typical rectangle, and we think about rotating that about the x-axis. And what are you going to get when you do that? Right? So the shape, first of all, the overall shape will be something like this. Oh, Nelly. How'd I do? Oh, come on. Rough crowd. Is it right? Yeah, with a hole in the top, right? So, is that, I'm thinking, so this is the shape, right? I got the right region? I'm rotating that around the y-axis. You're right, it's not my best. But I think it's right. I think it's right. Okay? So, then our typical shell is going to start from the typical slice like this, and it's going to go all the way around. So the shells with the smallest radius are going to be the tallest, and then the shells with the largest radius are going to be shorter. Okay, so we draw one shell here. Which is what you get when you rotate that little thing around the y-axis, right? So we need the volume of that shell. So it's going to be the circumference, which is be what you'd get if you laid that thing out flat, right? So 2 pi r times the height times the thickness. Which is basically just the volume of a rectangular solid, length times width times depth, right? Length of it is if we cut it and we unraveled it, then the length this way would be 2 pi r. The height is h, the thickness is that little thickness there. Okay? So what is our radius of our shell? What's the radius of our shell?
2 pi x.
Not 2 pi x. What is the radius of that right there? Just the radius. What coordinate is it?
X.
It's x. The radius is x. What is the height of the shell? Y. Okay, so the height of the shell is the y coordinate. And is the thickness delta x or delta y? delta x, right? Delta x is the thickness of the shell. So it's going to be 2 pi times the x coordinate times the height, which is the y coordinate, which is e to the minus x, times thickness, delta x. So there's the volume of a typical shell. And we're going to add all those shells up from what to what? Okay, how do you solve that integral? Undoing, you recognize that as undoing, you agree with product? Yeah. So that's the volume of the whole thing. Questions about that one? Okay, so let's try something harder. So now we're so the harder problems then would be combining skills from the harder problems of the discs and the washers, like figuring out radiuses and stuff, and then applying shells. Okay, so we have all the tools to do harder problems. We know how to do shells generally, and then we know about these harder problems of rotating around things other than the x and y axis. So we just got to put it all together. So let's try here number 17 in this section. I'll write it out. Here we go. Questions on this one? Are we good? Okay, so here we go. So we're going to find the volume, so I'll take the region bound by y equals 4x minus x squared.
What's that? You gotta
Is it for
erase the top half here.
No, it's not the height. It's the height of this, right? The height of your shell is the height of that. So it's y2 minus y1. So what is y2? Huh? And y and that. So we'll put it all together.
I'm still trying to like take it in. Okay. So for radius, so that'd be like from here to wherever you are here, right?
This is existence. No, star. We know it's not, and we have to find this
Okay.
Isn't it minus H? You know,
Okay, so did I do it right?
isn't it minus H?
Minus. Which one? The first or the second? First or second? Just checking. So I set up the volume of a typical shell for the first one. Did you get it? Okay, so now we're just going to get number 2 done. Questions on the first one? Okay, so okay. Which way is your slope? Okay, radius is going to be from the center of rotation to what? The y value of the
shell going in towards the center.
right?
Are you saying
So then that must be 1 minus y. Or y.
that's why it's stuck
Y greater than or less than 1?
if your radius is less than 0,
Y is less than 1. So 1 is up above, right? 1 is up here. Your y value is 1. Was it?
Minus y. Since you're just going straight down this line, because the radius is just the distance from here to like here, wherever you are.
No.
Okay, I've never had any complex plans, but I got it.
Yeah, so the radius, that makes sense, because your circle is going like this way. So from the center of rotation, it's just that. To wherever your rectangle is going to be the radius. So that's just moving up and down this line.
So I should have, you cut it open and you lay it out flat.
Since the area you're taking is
Width times height times thickness.
yeah,
It's not real inner and
yeah,
outer
so I see what you're
radius.
saying, like y minus 1
The
feels
inner
like
and outer radius is going to be like dx and dy. There's no, it's going to be really small. So there's no inner and outer radius. You're doing the volume of a rectangular solid that you get when you unplug it. Does that make sense?
no, see, because we're up here.
See, the thickness here is delta x. There's no inner and outer. It's going to get so small, right? It's going to get infinitely small. There's no inner and outer. It's just times delta x.
Because your y value is where you're at now, here, right? Like where you're at. So let's say that's at let's say 0.4.
Do you get second?
1 month. So say then, so y value is 0.4.
So we always start with center.
Yeah, it's got 1 minus y, because if it was 0.4,
Yeah.
we're going to say,
So the radius is going to. It's going to be. You have to calculate the positive value from the center to the shell, to the edge of the shell. You make a positive value. So it'll be. Yeah. I'll do number 2.
I think that's yeah, I think that's right, I said. Just one?
Yeah.
Wait, no, because then we have to. That's like what the. Because we have to work the y to the 130.
Just solve for
Versus solve for x, like in y. Yeah, like like get rid of y. Yeah.
So if we're gonna do shell's this way, is it going to be delta x or delta y?
That's just the circumferences. So
Okay? So we got that curved, like ramp triangle thing, and we're going to do a rectangle horizontally, and we're going to rotate that rectangle around y equals 1, and we'll get a shell the way I drew it. Volume of the shell, 2 pi r h delta x or y? Delta y. So we need the radius and the height of the shell. What's the radius? The radius is the distance from the center of rotation, 1, to here. The y coordinate of the curve. What's the height of the shell?
but isn't thickness the u line? Same line, either way, okay.
Okay, so what's the height of the shell? 1 minus x.
Okay. So
We need to get this in terms of y. What is x in terms of y? Did you get it? Okay, so we need to get out in a minute or two here. Questions? The height is from, listen up, she asked about how to get the height. The height of the shell is this distance right here, right? So it's defined by x equals 1 and what? The x coordinate of the point on the curve. Right? So it's the distance from the x coordinate of the point of the curve to x equals 1. So that's 1 minus x. And what is x? X will be what you get when you solve for x in that curve. So y to the 1/3. Other questions? Oh, so the integral is going to be in terms of y. Yeah, this is 1, 1, so you're going to go from 0 to 1. Okay, well, we're good tomorrow.